These lecture notes will be posted later on today. I know most of you like to be able to follow along, so apologies. Things have just been very hectic for me today. So today we are going to be talking about the fun topic of bending stress and beams. This is not something that is covered on your exam for Wednesday, but it will be on the following exam that's going to be happening a few weeks after break. So to start off, we've just got a few samples of some elements that might be causing, that you might see that aren't necessarily traditional bending. For example, one of the things is like, beams holding up roads. Yeah?
What chapter is this?
This is chapter 4. Yeah, we've done chapters 1, 2, and 7. There may be some interlude with chapter 7 moving forward as those stress transformation equations kind of become important, especially when we get into beam bending. So we will definitely be referring back to chapter 7 for some of the problems that we deal with in class. But generally speaking, I'd say we don't have to worry about that right now. We'll just be going over some of the general information for this. But anyways, when it comes to beams, most of you guys from your statics classes have remembered analyzing the reaction forces for certain elements and never necessarily saw or looked into the internal stresses that develop due to actual bending. The structures to form. You may have considered like pin reactions, roller supports, fixed reactions, but there's a lot that kind of goes into making those assumptions rather than just seeing triangles and circles. One such example is maybe like a clamp right here. If this was a beam being supported by 2 clamps on either end, that may actually be visualized as like a pin support, for example, because it allows some type of rotation under bending, but not a significant amount. Or depending on how much force is provided on the clamp, if there's any type of, maybe they attach more clamps to it, then you may end up with more of a fixed support or something in between. So ultimately, one of the important things to note is a lot of the stuff that we're going to be learning, again, we make a lot of engineering design assumptions, and the equations that you see here are idealistic. So just to start off, let's do just a quick recap. For example, you guys may have seen a problem that basically looked like this in your statics class, where you learned that to solve it, you would just do external equilibrium, which just comes from the sum of the forces in the x direction, sum of the forces in the y direction, and then sum of the moments, right? For this case, we have a cantilever reaction, so you guys should hopefully know that you'll have an AY, an AX, and then a moment, right? We know that for equilibrium, it has to equal 0. And so when we write out these equations, we end up with forces in the x direction is equal to AY minus P sine of alpha. Oh, wait, no, P cosine. Oh, I'm already messing up. Yeah, sorry, I'm thinking of like, oh wait, no, that's right. Just change that to forces in y and then forces in x. All right, for AX, you would have AX plus P cosine of alpha. And then for the moments, you would have MA minus P sine of alpha and then this would just be multiplied by L. Now from there, we can actually cut internal equilibrium, which then would basically just yield us, let me see if I can't just erase this now. Which then when you're analyzing the internal forces, you would just cut sections as we have been previously doing, and then you would get different equations through force equilibrium from there, which those equations would then you would end up with the internal force just equaling P cosine of alpha again. The shear force in the beam, V, would just be from some of the forces in Y, which would give you P sine of alpha. And then the moment that's inside the beam through force equilibrium, taking the moment about the cut, would just equal negative P sine of alpha. That would be the force that's applied. And then its perpendicular distance from the cut would just be L minus X. That's its positional coordinate on the beam. We'll do plenty more examples. I know it's a little bit confusing, but basically these internal force equations come directly from analyzing force equilibrium directly where you're cutting the beam, right? So you basically treat the cut as if it's a fixed end. Does that make sense? Awesome. So, specifically what we're going to be dealing with this lecture for this chapter is what we consider pure bending. Pure bending is basically when you don't necessarily have any axial or shear forces, but it's explicitly only internal moments within the beam. So basically you could think of it like if you have a pencil here and then you twist the ends, that would be considered pure bending. There wouldn't be any shear forces because then there would be no sliding. It's just pure bending. So pure bending occurs when the only internal force is what we call bending moment. We'll learn how to draw these diagrams later on, but you could think of it like, let's say we have a beam here, subjected to F times F located at distance A from either side. That region that's going to be within that beam would be subjected to entirely pure bending. I'll show you guys, you'll learn later on what pure bending looks like from an internal force diagram perspective. But it's basically when the moment is constant in a particular region. There's no variation, there's no moment that's subjective to a certain point. It's just pure. There's no shear forces causing any variation in the moment. So that moment, when you do force equilibrium, just ends up equaling force times the location where that force is applied with respect to the supports. We'll get into it a little bit later on, but the idea is that pure bending is basically where, again, the moment is constant. So the moment is constant. Or you could put in parentheses bending moment. All right. A good example of this where pure bending is not present is within a beam here, a cantilever fixed support. The reason being is because when you draw an internal force diagram, your bending moment is going to be maximum located here, and it's going to close out to zero here. And the reason for that has to do with some assumptions we'll learn later on, and I think it's chapter 5, where basically the bending moment is basically a function of the shear force. But what you guys will notice is the internal shear force, if we cut a section right through here, V, and then this reaction force is just going to be F, and then we ignore everything on this right-hand side, that shear force has to equal that force F. Does that make sense? So because of that, we get a shear force within the beam, which means it's not in a case of pure bending. So let me erase this just because I know there's some notes here. Clear pen markups. Whoops. And again, not working. Come on, there we go. So pure bending result will still apply for small deformations. We can use superposition adding the effects of shear and bending. This is something we'll learn later on I think, again, in chapter 5, where basically the summation of the shear force is equal to the bending moment at a particular point. I know that sounds like a lot, but it's actually a very simple thing. But our main focus right now is to determine how the stresses are distributed throughout the cross-section for a beam, right? So let's consider the beam here subjected to 2 end moments. Now, when you have a beam, and let's say you apply some vertical force or you twist it, is the beam going to be in tension, compression? What do you guys think? Is it going to be split somehow? Both? How so?
If you're bending a beam, would it compress towards the inner and then tension on the outer?
Exactly. So when we have this situation here, we're going to end up with compression up on the top. My pen is off. And then tension on the bottom. All right. Now, with this type of moment specifically, those sign conventions, this is what we consider the positive sign convention. Right? And that's typical for this case here. The reason being is because if we have, let's say, a fixed support here, and then that's the body of the beam right there, and we cut a section here, we want our moment to be clockwise. So always look at the moment on the right-hand side and draw it counterclockwise, and that's the positive sign convention. And then the opposite hand side always has to mirror that, which is why the left-hand side, even though it's a clockwise moment, it's still positive. Yep, that's just the plane of symmetry. Positive z moment on the x face and negative z moment on the negative x face. All right. Now, how do we determine all of our equations? First, we need to make some assumptions about how the beam is going to deform. So initially, we need to assume straight lines between AB and A prime, B prime. All right. Now, with those initial straight lines, once we subject them to some type of bending, we assume that because they're very small deformations, they are going to deform in a relatively circular manner, right? So because this section experiences the same moment, it's an infinitesimal moment, so we assume that there's no fluctuation at all. Not to mention, again, pure bending is when the bending moment is constant at a particular point. Every section should experience the same rotational deformation that's experienced. All right, so that section, all of those sections are all going to be the same deformation, which means that all of them are going to have some type of rotation. Of course, the bottom and the top are going to deform differently, but one of them is going to be in compression, one of them is going to be in tension. And the important thing to note is that the strains, if you guys remember from three-dimensional stresses, the lateral strain is independent of direction. It's a very similar case here. You have the strains, which are the same roughly at the top and at the bottom, depending on the geometry. So we assume that AB shrinks in length, and then A prime, B prime on the bottom is going to grow because of compression on the top, tension on the bottom. And then lastly, we define some center point C, which is, of course, the center of rotation, which is going to be the point that we're going to use for the derivation of all of our equations, assuming circular arc lengths. All right? So moving forward with this, we basically analyze the strains and the stresses at a particular point. We can look at some cross-sectional point of view, and basically what we should find is if we look at the stress block on a particular point, let's say, so we'll look at it from this perspective here. I want to change my pen color to black, right? let's say we look at the stress block that develops along the top here, right? So let's kind of go into our Moore circle perspectives. Let's just draw some rectangular block, look at it from the XY plane. Because we are considering pure bending, there should be no shear force, which means no shear stresses. So what we should get is that tau xy is basically equal to 0. In a similar way, there should be no vertical forces being developed or lateral forces. So sigma y and sigma z are also equal to 0. Which leaves us with just sigma x, which basically sigma x is basically going to be a non-zero value, right? Because if we're dealing with compression, then technically the sigma x is going to be negative at the top, and then it's positive at the bottom. And then, of course, looking at this small section over here, we can decipher that the strain that's basically felt, this gamma xy, again, shear strain, there's no shear stresses or shear forces developing due to pure bending, has to equal 0 also. So, moving on with this, we need to look at equilibrium in order to decipher the stress equations, all right? So, we look at the sum of the forces in the x direction, and the sum of the forces in the x direction is basically just going to equal the sum of all of the stresses multiplied by their perpendicular areas, right? We learned this from very initial part of the semester, which we can then just generalize it more to an integral over some particular area of sigma x times dA, and then this equilibrium has to result in 0 because it's an equilibrium. Now, another thing we want to do is we want to take moments about y, all right? And from equilibrium, what we should find is that this is just going to equal the integral of sigma x, and then this stress here is technically going to have a perpendicular distance z if we're dealing with some type of eccentricity. So we need to multiply that by z, and then that gets integrated by the area, which again has to equal 0. Again, if we're dealing with a perfectly symmetric cross-section, guess what? That z doesn't exist. Z is like an eccentricity, consider it, you can say. Like if you have a very non-symmetric cross-section, like for example, you guys ever see like steel channels, for example? Something like that would produce some type of stress eccentricity within the cross-section that you would need to consider. But if you're dealing with something like an I-beam or like a 2x4, that z is not going to be present. So this is really going to be only for non-symmetric cross-sections, which let me just... And then lastly, just in general, the bending moment about the z-axis, which is going to be our state of pure bending, assuming no eccentricity, is just going to equal the integral about the area of sigma x times negative y dA, which this is equal to our bending moment within the beam. Now, you might be wondering why we still have tau xz dA and tau xy dA. It's because when you do the force equilibriums, the sum of the forces in x, sum of the forces in z, and the sum of the moments about x are the only ones that depend on tau xz and tau xy. Whoops. I said tau yy. So these will shortly vanish. Just because of the fact that they're not really going to be accounted for within our general state of bending. Let me know when I'm good to continue. All right. Just going to give it a minute, actually. I think everyone else is writing. All right. So, some of this is still still dealing with some of the printouts and such. So from the sum of the forces in the x direction, when again we integrated from over the area for sigma x dA from equaling 0, when we analyze all of this, we find that basically the stress that we get that's negative basically just indicates compression, and then the stress that's positive indicates tension. So negative compression and then positive tension. And then both of these have to exist over a portion of the cross-section. So that's where we get this stress distribution right here. What you guys will notice is it's linear, and we are getting that the stress is compressive up on the top and tensile along the bottom. All right, so it's a linear stress distribution that we are considering. And what is important to note is that the summation of the compression and tensile forces, which is basically the area underneath the stress diagram, has to equal 0, right? So if all of this is basically, let's call it C and then T, then through this force equilibrium, C has to basically equal T. Make sense? Now, there is a surface where, again, you might be wondering what that neutral surface is. The neutral surface is the point where there's technically no stress, all right? So we call this the neutral axis. You guys have maybe heard of this term. Have you guys heard of this term, the neutral axis? Have you guys heard of centroids for a cross-section? That's the neutral axis. That's like if you guys were dealing with a rectangular shape, the centroid is dead center in the middle. That's basically the location of the neutral axis. There's a reason why you guys did that in statics, and that's because that is a very critical point in determining what the stresses, how they vary, because that is a known point of what the stress is. Right, so let me clear these markings. Again, the neutral axis, we can determine what the neutral axis and where it's located just through some statics. We'll do some examples just showing you guys how the stuff you learned in statics is applied, but hopefully everybody should understand how to do it. Right? So let's consider what we've learned so far and understand how we can kind of relate everything we've learned so far into the deformations that the beam is basically going to feel under a case of pure bending. So again, as I mentioned, along the neutral axis, we know that the strain is not going to be present. There's no strain on the neutral axis because it's a point where it's no stress. No stress means no strain. So on the neutral axis, NA, we know that the strain, which we're looking at an XY plane, so I'm just going to say the strain in the X direction has to equal 0. From this, we can kind of convert this to an arc length equation. Who here knows how arc lengths work? You guys do? So we can kind of decipher an entire length for what this beam would be. So the length in the X direction would just be defined as this term rho times theta, which rho is basically just the radius of curvature, and then theta is just the angle for the segment that we're considering, right? Now, let's take a look at some arbitrary point that we're interested in. This arbitrary point, let's say, is that line JK, which is the dashed line that's shown right on the diagram. We know that the length just becomes some arbitrary adjusted length, L prime, because again, it's being compressed or tensed depending on where you're looking at. You know, in this case, we're going to be able to see that it's actually kind of being compressed a bit. So this equation just then becomes, instead of it being rho, it's just going to be rho minus y. And then again, that theta is constant because, it's the radius of our subtended segment. Now we can calculate what the change in length is going to be. So that delta for JK is basically just going to equal L prime minus L, which then when you do the math, you'll find is just equal to negative y times theta. Now we can calculate the strain knowing that the strain is equal to what? Deformation over the initial length, right? So it's equal to delta JK over L. I'm going to call this, it's just L. So it's negative y theta over rho theta. The thetas are going to cancel out, which means that the strain is just equal to negative y over rho. And that is equation number 1. All right, so, sure thing. And then I'm just going to note arc length equation. Everyone follow along so far? Awesome. All right. So, again, our strain in the x direction is just equal to negative y over rho. And so now we can have this is expressed as just a general function if we wanted to find the strain at any particular point along the cross-section of the beam, perpendicular to the cross-section, of course. We could just plug in some value of y, knowing what the radius of curvature is. Now, if we wanted to find the maximum strains, the maximum strain, which we call epsilon m, is just going to be basically wherever the top and bottom are. Whoops, that is disgusting. Yikes. Right, so in this case here, if we wanted to find the maximum strains, we would consider C, H minus C. So this would just basically be, let me kind of rewrite this a bit. Whoops. Epsilon max is just equal to the max of negative C over rho, or negative, if this entire cross-section is some height h, negative h minus c over rho. So it's one of the two. Basically, the two critical points are just here and here. Now with that in mind, we can now relate this to calculating the stresses. What is stress equal to? P over A, but how is it related to strain? Exam 1, guys.
Strain times young.
Yeah.
Exactly. That's called Hooke's law, right? I don't even know if I spelled Hooke's law right. I think there's an E in Hook.
Yeah.
Just so I don't get. Hooke's law, we know that stress is equal to the strain times the elastic modulus. Elastic modulus is a known material property. We can then rewrite this to just say negative E times Y. I know that's an atrocious Y. Y over rho. And then again, the maximum stresses would just be similar to the maximum strains, where you would just calculate whatever's on the top and bottom. So you could just calculate whatever the strains are and then just multiply it by E to get the stresses. All right. Are there any questions about anything we've covered so far? Let me ask this. Is everyone at least liking this a little better than me sliding through the different presentations with the texts? You guys are following along a bit easier, right? Instead of all the text being all jumbled and messed up. Yeah, this is a lot easier for me too. All right. Now, location of the neutral axis. We need to basically use sigma x is equal to negative E y over rho in our equation for the sum of the forces in the x direction, which again is defined as sigma x times dA, which is equal to 0. E and rho are going to be a constant, so we can factor it out of the integral. So what we get is negative E over rho times the integral of A y dA is equal to 0. Does this part of the equation look familiar to anyone? It does? Awesome. Great. So let me just erase this really quickly. Right, so what is YdA? Anybody have a guess on what YdA is equal to, or that integral? Anyone remember it?
Is it the center?
Yeah.
Yeah.
So, just moving forward a bit more with this. Oh, I think I accidentally skipped a slide, but either way, using this integral, yeah, we know where the centroid is. All right, we can use a similar thing where if we use sigma x again in negative EY over rho, we can use this in our sum of the moments about the z-axis. And we know that this has to equal the bending moment within the beam, right? This is the really important equation for this chapter. From this integral, we would get that the bending moment in the beam is just equal to E over rho times the integral of A y squared dA. Does anyone remember what this equation is? What is it? Moment of inertia. So we can rewrite this to just say EI over rho. Now, some of you may have seen, who here's taken dynamics? Okay, some of you have. So hopefully you guys have seen the curvature equation before, where we define our K curvature equal to 1 over rho. Have you guys seen that before?
In calc, not dynamics yet.
Okay, I might be jumping the gun then a little bit, but yeah. So we define that, and what we end up with is that, well, I should maybe just, we can rewrite this to then just define a term for rho, which is just equal to EI over M. And then, of course, the curvature equation is just going to be M over EI. Lastly, by just using this, we actually solve for the stress in the x direction, where we get the equation negative my over I. And that comes from relating the curvature and the strains to that equation rho that we had previously determined beforehand. So now we have a stress equation to relate internal bending moments to geometric coordinates. All right? Now, there is one note that I want to make is in some cross sections, some standard cross sections like I-beams, or in like maybe you guys have seen them when you were doing your second moment area of inertia section in statics, you may have seen some term we call S. We call that the section modulus, elastic section modulus. That basically just gets defined as I over Y. Oh, my pen is not writing. Oh, there we go. Oh, I think my pen is dead. Interesting. Let me see. Something. That's very unfortunate. I think I can use the mouse to write, but please excuse the atrocious handwriting. I'm going to try my best. Right, where S is just equal to that term I over Y. And that's just for standardized shapes. You see that very commonly when you're dealing with I-beams where they're doubly symmetric. If you're dealing with non-symmetric shapes, it's better to use the Y over I equation, because then trying to find an S value, you're going to have two S values anyways, because then the Y value can vary significantly.
Would you say S was called?
What?
Would you say S was called?
It's called the elastic section modulus. Please don't make me write it out. Actually, I'll just write it out on the chalkboard. And this is going to be in units of inches cubed or millimeters cubed, basically whatever unit of measurement cubed. All right, have a good one. All right, so this equation becomes very useful when we learn when we remember how to calculate the second moment area of inertia for a rectangular cross section. What do you guys know is the second moment area of inertia for that? Should be a memorized value at this point. Hopefully you guys have seen it so many times. 1 over 12 what? It's not just 1 over 12.
BH cubed.
BH cubed, right? So there's standardized tables for all of this. So 1 over 12 BH cubed, right? But where does this come from? Hopefully you guys remember that you need to calculate I, integral of a y squared dA, which then, oh yikes, that is atrocious, dA, which again just comes from a double integral where we have negative b over 2, and then, I don't know why I wrote 3. Crud. Sorry. Negative b over 2, b over 2, and then h over 2 to negative h over 2, y squared, and then this is integrated by dy and dx. And now our first moment area of inertia, which is what I was trying to explain earlier, our QZ is just at a y dA, which is just going to equal the integral from negative b over 2 to b over 2, integral from 0 to h of y times dy dz. That should not be dx, that should be dz also. Which, when you're solving all of this, you should find that basically that y bar value comes as h over 2, and then this iz is basically equal to bh cubed over 12. So they don't just come from a table. There's a mathematical meaning behind it. I could give you guys a cross-sectional area in terms of cosine if I wanted to be a real jerk. I don't think I'll do that. All right. Now, with this in mind, which side is stronger? Left side? Why?
It's got a bigger height to it, and now it's cubed.
Exactly. So the EI is just going to equal, well, actually, let me take a step back. So one of the ways that we can define why it's stiffer is through what we call flexural rigidity. Which is just equal to that EI term that I just kind of just wrote without any explanation. And basically this EI term comes from another variation of the internal, of like the spring equation, where you can consider M is equal to EI times K, where K is, again, our curvature function, 1 over rho. EI would be kind of like the stiffness of our material, and then M is the moment. So in a similar way, this is kind of synonymous to the F is equal to K times delta equations that you guys have seen in like your physics class, or that we've kind of dealt with early on in the class, right? And so one way that we can kind of quantify the stiffness of those two sections is through this EI term. So for this section here, if we write out everything, it would just be 1 over 12 times EBA cubed. And then for this one here, it would be 1 over 12 EAB cubed. Right? So the stiffness is not only dependent on the cross-sectional property, but it's also dependent on the material property as well. So if the left-hand side was made out of wood and then the right-hand side was made out of steel, you can't exactly just say that the one on the left-hand side is stiffer. You would need to actually figure out mathematically which one is stiffer by understanding the material properties and the cross-sectional properties in the cross-section. Are there any questions so far about what we've discussed? None? Awesome. let me ask this, all right? We went over previously what the section modulus is. S was just equal to I over Y. So we can look at the section moduli for each of these, right? We determined previously that I for this was equal to BA cubed over 12. Let's say that the point of maximum stress would be where? Where would the point of maximum stress and strain be located? Yeah, top and bottom, which for a symmetric cross-section would just be A over 2, right? So Y for max would just be A over 2. So we can calculate what the section modulus of this would be by just plugging in BA cubed over 12 divided by A over 2. And what we are left with is BA squared over 6. This may look familiar to you guys if you have seen tables involving this S term. It may not look familiar to you guys. But yeah, so if you guys had a rectangular cross-section, instead of calculating I and Y, you can just straight up use an S term. Some formula sheets will have the S term, so you guys can just plug and chug directly into that. In a similar way, we could follow all of the steps that we did previously for that, and we would basically be left with Y max for this equaling B over 2. I is equal to AB cubed over 12. So this would just be B squared A over 6. Now, let's say we had just some rectangular block. How would you guys want to increase the second moment area of inertia and in turn the section modulus without changing the cross-sectional area? Yeah.
Or like not changing the shape or just the amount of area?
Not changing the area. You can change the shape however you want.
You want to have more of the area further from the axis of rotation or the bending like the
Exactly.
Yeah.
One of the things you could do is increasing the height of it, but in turn making it thinner. And so when we do this, we actually find that we can actually hold more capacity. And that's actually why when you're looking at steel structures, you actually have that I shape. The flanges are placed at the top and bottom, which then allow you to carry more of the bending stresses. Because again, when we look at the bending distribution, the maximum bending stresses occur at the top and the bottom. So you have more area at the top and bottom in order to carry those bending stresses. And then that long horizontal section there, we'll get into it a little bit later on, is able to carry a lot more of the shear forces that would be opposed on them. So that's why you see a lot of American standard shapes and wide flange beams all over the place, is because their geometry is very unique. And again, this is like one of those examples of seeing that section modulus term within design tables. That section modulus term, you'll see, is that SX and SY value, where the section modulus about the x-axis is basically just the section modulus for bending about the x-axis. Are there any questions about this at all? How we may use those design tables at all? All right. Now, next slide, I go into a little bit of it and provide just generally a summary, and then we'll hop straight into like an example of how we would use this. So just as a short recap, under pure bending, axial straight lines become arcs. So I just spelled straight wrong. I'm an engineer, not an English teacher. So under pure bending, straight lines become arcs. The neutral axis which we determined was that term y bar that you guys learned from your statics class, is location of sigma x equals 0 and epsilon x equals 0. For positive bending, tension is on the bottom. And then lastly, the neutral axis passes through the centroid of the cross section. Which we defined as that y dA equals 0. And then continuing, let me just let you guys write this down really quickly. All right. And then just as a recap for all of our equations, epsilon x as a function of the y coordinate is defined as negative y over rho, with its x stress equaling negative my over I. The maximum stresses and strains occur at the furthest point away from the neutral axis. Which is the location from neutral axis. We can summarize this for symmetric cross sections, the stress equation, to be equal to negative m over s, where s was equal to I over y. Or better yet, I'm going to say instead of y, it was equal to I over our coordinate c, because c was the location furthest away from the neutral axis. I'll put equals c there for max value of y. So the max value of y, whatever it is just going to be c. And then the curvature equation k was equal to m, the internal bending moment, divided by the flexural rigidity, which again is also equal to 1 over rho. Yes?
What's K again?
K is curvature. And then rho is just radius. Don't ask me why the textbook images use rho as the radius. I would have preferred r, but yeah. All right. Now to finally see where something like this is applicable. All right. We want to calculate the maximum stress and bending curvature on the beam that's shown. I'll give you guys a minute to solve for it, or not solve for it, but just to write down the problem. As I take a nice sip of coffee, because I'm addicted to it. You guys will be living off of coffee in the future. I'm even just gonna want to simplify this slightly. I don't want you guys to use these numbers. Don't even bother with the numbers. Just write a general calc for it. Because then you could just go into Excel and plug in any number for anything. As long as it's positive, of course. Does everyone have the shape drawn out and the image written, or the problem written? Because I'm about to change to another slide, just to give you guys a little bit of help with solving it. Let me know when I'm good. All right. You guys will need this to solve for it. Hopefully it's somewhat visible. Freeze the... And let me check the syllabus, actually. Let's see. Awesome. We're right on schedule for today. Try and calculate what the supplemental area of inertia is of the cross section, and then from there you can kind of figure out everything else. But that's generally the rule for solving any deep problems, figuring out I and exactly.
Sure.
There we go. Give it another minute.
So let's go over it.
All right. How many of you wasted your time calculating the centroid? It's a symmetric shape. It's a important thing to note. It's always going to be, if you have like it's symmetric. So the centroid, if you guys looked carefully enough, y bar is just going to be at a plus b divided by 2. Everyone sees that, right? The hard part is getting the I term. I always like to use the tables that Professor Dawson taught with. So calculate components, areas, dy, a dy squared, and then ix. Now, there's a few ways that you could have broken this up. You could break it up into a top flange, a web, and then a bottom flange. You could have broken it up as 2 rectangles, one just being a rectangle of 2d plus c times 2a plus b, and then subtracting that negative area that's there. There's several ways you could have really done this. I am going to use 1, 2, and 3. So top web, top flange, middle web, bottom flange, 1, 2, 3. And basically the areas for 1 is going to be A times 2D plus C. For 2, it's going to be CB. And then for 3, it's going to be a times 2d plus c. dy is basically just going to equal whatever y bar of each component is minus the total y bar. So in this case, it's just going to be equal to whatever y bar I is minus a plus b over 2. So for component 1, that's going to be y bar 1 is just going to be a plus b plus a over 2. So then when you subtract that, I hate letters, but I tried making it nice. I don't know why I'm grabbing a calculator. Let's see. A plus, all right, so we're not going to have an A. We're going to have a B over 2. So it's going to be what? Y bar 1 is equal to B over 2 plus A over 2? Is that what everyone gets? Somebody confirm that. Somebody fact check. Let's see. A plus B plus A over 2 minus A minus B over 2. That A cancels with that A. That then just makes this B over 2. So yeah, B over 2 plus A over 2. All right. So we've got B over 2 plus A over 2. For 2, dy, the centroid of that is actually directly in line with the neutral axis. It's right on the neutral axis because it's symmetric. So it's 0. And then for 3, it's just going to be A over 2. Let's see. We've got y bar 3 is equal to A over 2 minus A plus B over 2. So it looks like B over 2 minus A over 2? Yeah. All right. You would just carry out the multiplication, which should give you, I want to say, oh gosh. All right. A times 2d plus c times b over 2 plus a over 2 squared. Let me erase all of this. Then this is going to be a times 2d plus c times b over 2 minus a over 2 squared, 0. And then your ix term is just going to be, for 1, 1 over 12 times 2d plus c times a cubed. Same with this. And then for the section 2, it's going to be 1 over 12 times c times b cubed. All right, so then everyone remembers this parallel axis theorem, right? So, whoops. Let me know when everyone's got this written down, because I'm about to erase it and continue on. All right. So let me clear all of my markings. Basically, from the parallel axis theorem, the total Ix is going to equal the summation of all of the Ix's plus the summation of all of the a dy squareds, which when you do that, you should get 1 over 12 times c plus 2d, sorry. Please don't erase. erase, plus 2d times b plus a cubed minus 2 times 1 over 12 times db cubed. That's what it simplifies to. All right. From there, we want to find the maximum stress location that's going to occur at that point C, which is the same as our Y max value, which is just conveniently going to be A plus B over 2. That is this dimension here, so that's C. And of course it's plus or minus, so put that at the front. All right, I put it in the back just because I don't have room. All right, and then lastly, we can calculate the stress by just plugging in MC over I, which is just going to equal M, which is going to be a known value. We'll always know the bending moment from internal equilibrium. C is going to be A plus B over 2. And then I is going to be this giant term, 1 over 12 C plus 2D times B plus A cubed minus 2 times 1 over 12 dB cubed. It looks a lot cleaner with numbers most times. All right. The example that's in this lecture is not exactly the most fun one, but next class I'll maybe try and get some actual live examples for using design tables and so on and so forth for how we would calculate the bending stress. And then, of course, figure out how to design knowing the certain stress parameters of given material properties. All right, that's going to be it for today. If you guys have any questions, let me know. Otherwise, yeah, next class is your exam. I'm wishing you all luck. Don't worry, it's not too bad. All right.